So I'm going to start my recording now. So this is the paper 3, which you've had a few goes at, but I would like you to give this one last sort of stab. At the moment, what I'm doing is I'm collating a lot of the assessment data from a lot of the things that have been handed in to me. And the idea is meant to be that I can use that to try and help inform my grades a little bit in terms of the grade that I submit to the exam board. I can't discuss your individual grades with you, I'm not allowed to do that. But the purpose behind this is that although I have to treat anything submitted, obviously that's not under exam conditions, I have to treat it with a little bit of caution. It can help inform the grade that I award for you. Okay, so we're going to go through paper 3. You've done a few paper 3s before, but as I said, I'm just going to talk you through some of the parts of this. Now, obviously, being a practical paper and being at home or being in your rooms, you can't really do the practical itself. So what I've done is I've done the practical and I've put some data in for you. So anywhere where there's a measurement, there'll be some data. So if we go through this, we start with question number 1. It tells you that you're investigating the motion of a chain of paper clips. You're provided with a chain of 15 paper clips with a sphere of modelling clay, otherwise known as plasticine or blue tack, at one end of the chain. You have to measure and record the length L of one paper clip as shown. So you record the length of the paper clip, obviously not this one, this is expanded. Now when I did the experiment, the paper clips I used were exactly to the millimetre, 4 centimetres long. So I've written that in for you, okay? Notice in here, we've kept our decimal places correct because we know it's plus or minus 1 millimetre, which is the same thing as being plus or minus 0.01001 meters. Okay, so even though it's 0.04, I have to say it's 0.040 meters. So I've put in my unit and I've put my value to the correct number of decimal places. As we move on, we start to get to the experiment itself. So it's a pendulum experiment, basically. You've got all your paper clips all joined together here, and you've got your plasticine sphere here. So it's a pendulum, but it's got a wooden rod. So what happens with this one is you've got your sort of secure end at the top. You've got your pendulum, but it's interrupted here. So what happens is that when it's on half of the swing, it's a long pendulum, and when it's on the other half of the swing, it's a shorter pendulum. So it sort of interrupts itself. It means it doesn't behave like a plain simple pendulum. You don't need to know the physics behind it for this exam, but it's quite useful to understand that actually the time period would be well, for a pendulum, we know it's 2 pi. We know that the time period for a pendulum is 2 pi times the square root of L over G, length over gravitational field strength. But that's for one half. But what happens is the other half, that length is a lot shorter. So the time period is shorter. So basically half of the swing is that, the other half of the swing is that. So what it is it's half of the time taken for the pendulum to go from here to the maximum and to the middle. So it's half of that. So half of 2 pi is simply pi times the square root of the length over gravity, plus the other half of the swing, which is the time taken for the pendulum to go from here to here and back again. So that's half of 2 pi is just pi, square root of, well, it's going to be a different length. This is, I call this L with a dash. So that's L dashed over G, okay? That's the physics behind this particular experiment. You don't need to know it for the experiment, but it's kind of useful, I think, with Unit 4 and also with further study with physics. It then says the chain should be suspended from the nail, as it is there. The wooden rod should be positioned so that when it's hanging vertically, the chain just touches the rod, and there are 6 paper clips below the rod. And you then have to record the number N of paper clips below the rod. Obviously, that's 6. Now, when you then you have to work out the time, you have to measure the time period. So you move the sphere towards you through a distance of approximately 10 centimeters, release the sphere, and the chain will oscillate and hit the rod during these oscillations. You have to determine the period T of the oscillations. So obviously you want to measure the time for 10 complete swings, for 10 complete oscillations. That's to go from the middle to the end, to the other end, and back to the middle. So really you would place here a fiducial marker so that you would start and stop your stopwatch as the pendulum passes that marker. Obviously, with any measurement, you don't want to do it once, you want to do it 2 or 3 times. I did it 3 times when I measured it, and I measured the time for 10 swings is 28.8 seconds. So my time for one swing for one oscillation is 2.88 seconds. You'll have to divide it by 10. So the bit that's missing here is, of course, the unit, which I expect you to put on. In this question, you'd get 1 mark for correctly measuring the time period, 2nd mark for doing some form of repeats. On to the next part, which would be then, as per practical, you have to change N by moving the wooden rod vertically and repeat B and C until you've got 6 complete values of N of the number of paper clips below the rod and the time period. So I've done this for you, where I've counted the number of paper clips below the rod. Now I've tried to use here a maximum range, okay? So I've tried to go from maximum to minimum. The trick is that when you actually look at this diagram, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 paper clips. Now, if you've got 15 paper clips, your extremes are 4 and 14, because that would place the rod up here, and for 14, and it would place the rod, well, it's 4, so it's 1, 2, 3, 4. You place the rod about here. Any lower than that, then you'll start getting problems with accurately measuring the time period. It'll stop following the pattern because you only have 1 or 2 paper clips, and it won't bend properly. So that's what I did. I measured the time for 10 swings. As per any good physics, we also look to do it once, twice, 3 times to get a mean value, okay, for 10 swings. Then you divide it by 10. You must show somewhere the calculation, any calculations that you do. So quoting the formula here is fine. You've also made sure that you've got the name, the symbol, and the unit. Here the number of clips is just a number, so it doesn't have the unit, so the square root of the unitless figure is still unitless. But here the time's in seconds, time period in seconds. I'll make it very, very clear. Now the bit that's going to take up some of your time is going to be recording the plot of graph T on the y-axis versus the square root of n on the x-axis. A lot of candidates, when they did this for the real paper, they forgot to square root the n and they didn't get a straight line. Now you draw the straight line of best fit. So what are we looking at here? Well, first of all, we've got to look at the scale. So if the square root of n goes on the x-axis here, we want to make sure that we use as much of the paper as possible, even if we don't have a 0 origin here. In fact, it's going to start off at 2, because square root of 4 is 2, and it's going to end at just before 4. So you go 2, 3, 4, that would be tiny. So maybe it's 2.5 squares. 2, 2.2, 4, 6, 8, 3, 2, 4, 6, 8, 4. Again, that's still a bit too small, but I think it's as good as we're going to get unless you turn the paper around. So you could then measure, you could then set your scale. Remember, you get a mark here for your scale, your labels. Remember, it's going to be name, symbol, unit. You get marks for your plot for plotting correctly, and in the real exam, the examiner actually checks that you've plotted some of those points correctly, and then you get your line of best. Whoops, it's gone off the bottom of the page. You get your line of best fits. You don't have to do a worst one. This is not a paper 5. I think you guys have mastered paper 5, so we're not dwelling on that. So you're thinking about your scale, you're thinking about your units. You know that you've got to measure time period. Well, the time period, I can tell you very, very roughly. You've got to do the calculations here, but the time period is therefore going to be between 29 and 30, well, about 32-ish, okay? So we've got to think about how we're measuring this. So 29, if we do 1, 2, 3, 4, 5 up to 30, 1, 2, 3, 4, 5 up to 31 doesn't fit, so you have to try and work out your scale here. So maybe 1, 2, 3, 4 would take you up to 30. 1, 2, 3, 4. Well, sorry, 1, 2, 3, 4 would take you up to 31. 1, 2, 3, 4 would take you up to 32. The average of 31.5 and 31.2 and 32.3 is below 32, so that works. So you'd probably want to go up in 4s. So every 4 squares represents 1 second. Okay. You then draw your line of best fit. You plot your points, sorry, and then you draw your line of best fit, which should have the same number of points above and below the line. So when you're plotting points, a lot of people, when they plot points, they put a little dot like that. We don't put little dots like that. If you use a dot, if you find yourself using dots in an exam, just draw a circle around it to make it clear that that is actually a data point, not just a bit of ink. You could also use a diagonal cross like that to measure your data points. In the actual graph drawing, the examiner also insists that your data points are quite small, so you should use a sharp pencil. Examples that definitely don't fit, so those are the correct way to do a data point. What's not correct are things like that, just a simple dot like that, or big splodgy crosses like that. Basically, those would not get your plotting marks because you've not done it correctly. The examiner insists that you are usually within about 1 millimeter, which is half a small square, when you're actually doing your plot. So the next stage is then to measure the gradient, determine the gradient of the graph. So again, when you're determining the gradient, what have you got to watch out for? First of all, they want to see that you used a big triangle. They give you, it's 2 marks for the gradient and intercept. If you don't draw a big triangle on your graph, oops. If you don't draw the big triangle on the graph, you won't get the mark for measuring the gradient because the examiner doesn't know how you did it. Then they want to see the idea of using the idea that you're measuring a gradient, delta y over delta x equals y1 minus y2 over x1 minus x2, etc. So you need to then measure your gradient. Then to get the intercept, it is unlikely on here that you'll have the 0 origin there. So you should use y equals mx plus c, the mathematical formula for a straight line graph. Calculate that c is equal to y minus mx, and again you need to read y and x from the graph. Okay, so again, you've got to show it. Don't just read random. Don't just read the value off the graph. Actually put on those working lines to show exactly where you got that number from. The examiner is not in the slightest bit interested in what those actual values are, as long as they're correctly calculated. What they're interested in is the use of this technique. If this technique is not evident, you don't get the marks. So it's quite important to show a technique. Moving on to the other part of question 1, you've got a suggested formula, and it says use your graph to give the answers to work out what P and Q are. Well, you know that time period goes on the y-axis. You know that square root of the number of paper clips goes on the x-axis. So the gradient is P, and the intercept, the y-intercept, is Q. So P is going to be your gradient. Q is your y-intercept. Okay. Now you've got to actually. I would put that on. I'd put that on because it's worth 2 marks. You've got to recognise that, and then it's exactly the same numbers as the values here. Now you've also got to think about what the units of P and Q are. So you think about what the gradient, how you measured the gradient. The gradient is delta y over delta x. So on the y-axis, it said you have to put t, time. So the y-intercept is going to be in seconds, and their p is the gradient. So the gradient is y over x. So it's seconds divided by no units. So that will also be in seconds. You then have to use your gradient to get a value. So it says p equals pi over the square root of L over G. And this is just a one marker. It's very easy to do. So what you'd have to do is you'd have to identify that P is your gradient is equal to pi times the square root of L over G. So G, so to work it out, you've got to square the gradient and square pi. So it's a gradient over pi. And is it? Hang on. So G would be up here. So you have to square it all first. Okay. Then you make G the subject. So G has to come up here. Gradient squared has to come down. So you end up with pi squared L over the gradient squared. Okay. Then you substitute, and then you put your numbers in here. Now it says here, give an appropriate unit. So we've got to think about what the units are. Well, if the unit for gradient is seconds, that's going to be meters per second squared. The other clue here is you're determining a value for G, where G is the acceleration due to free fall. It's acceleration, so you are expecting that to be in meters per second squared, which you must put there. It's a very easy mark if you just follow the procedures. Remember that even if your value for G is wildly different from 9.81, which it should be, you still get the mark, because the marks aren't for the answer particularly. The marks are for the use of your technique, and in this case also the units. If you don't put the units on, you lose the mark, which is a silly thing to lose a mark over, really.
Mr. Gary.
Yep.
Yeah, sorry to disturb you. Can you go over how you got the y-intercept?
How you get the y-intercept? Right.
Yeah.
So the y-intercept, if I show you on here, you get y equals mx plus c. So if I find I'm just going to find a piece of blank paper. Here we go. Got some note paper here. Bear with me. If you've got a gradient, if you've got a graph with a particular gradient, y and x, you get a y-intercept. The mathematical formula for a straight line is y equals mx plus c. You know, m is the gradient and c is the y-intercept, which you've asked me is how you find that. Okay, so you rearrange first of all to make the y-intercept the subject of the equation. So c equals y minus mx. Do you see that that's just a that is just a rearrangement of that?
Yes. Okay, I understand.
Okay.
Now. Okay.
So what you then do is you actually pick you pick a convenient point on your graph, just like you do with your two ends of your graph, two ends of your triangle, which must be more than half of the line. You pick sort of your y1, your y2, x1, and x2. You can call them anything you like, really. I prefer y1 and y2 just because it's a bit neater and easier to remember. But then what you do is you pick another value of x, which you draw your line up, you read across to y, and you get your corresponding value of y. And the x and y in there go into the x and y respectively in here. So you've measured your gradient. So you've got all your values to find out what c is, what the intercept is. Does that make sense?
Yeah, it does. Thank you.
That's good. Thank you for asking a question. I appreciate people who ask questions. So the next part of this to do is going on to question 2. Now, obviously for this one, you need to use your imagination a little bit, because again, we're not doing the experiment for real. I've done the experiment and I've given the values to you. So the first bit's academic, really. You're measuring the record. You've got a big long meter ruler with 2 holes either side, with a hole either side of it, either end of it, and you're measuring the distance between the centers of the 2 holes, which you would do using the scale. Okay, so this might be at say 0.005 meters, and this will be at 0.995 meters. Okay, and it'd be the difference between the two. Now, thinking about it, if you're measuring it by looking at the scale on the meter rule, which is what you should do, you should recognize that that's going to be plus or minus 1 millimeter. It could be plus or minus 2. Okay, doesn't actually matter. You can use 1 or 2 in this case. So you're then setting up a pivoting experiment. You're balancing your 100 gram mass and your 50 gram mass. You have to work out where the balance point is by just moving it, and then you measure that balance point. Really, you should do this twice, but I've only done it once because I just wanted to give you the value of 40 centimeters going from here to here. And what I've then done, what it then asked you to do, was to add the 10 gram slotted masses to each mass hanger. So this is now 110 grams. This is now 60 grams. So the balance point is going to shift slightly, not by a lot, but it'll shift a bit. Okay, so you find your new balance point and you measure Y, which I've measured here. Now, here's where we've got to think carefully. We're measuring Y again. We could say that's plus or minus 1 millimeter, but I've got it in centimeters there, so it should be 0.1 centimeters. We calculate Y minus X, so you get your previous value on the previous page, and it's the difference between the two. So when you're then measuring Y minus X, you put it there, and then it wants your percentage uncertainty in Y minus X. You can use upper and lower bounds, but it's simpler to understand that if you want to know the uncertainty in any two values added or subtracted, that's simply going to be the uncertainty in Y plus the uncertainty in X. Now, to get the uncertainty, there are two ways of doing it. If you only measured once, which I've only done here, that's going to be plus or minus 0.1 centimeters to get the uncertainty. So that would be added together. If you repeated, if you did it twice, then obviously it would be the difference between the two values divided by 2. Okay, but here we're just going to keep it simple. We're adding the finite uncertainties together. Then it wants the percentage uncertainty. So you find out what the absolute uncertainty between the two is, and then divide it by whatever your answer is. Multiply it by 100 as an option if you want to express it as a percentage. You can express it as a decimal if you wish, but you've got to be clear in your working so the examiner can see that's what you did. Okay? So on to the next part. You've then got to calculate. It says calculate M equals A minus 2Y, where M is 10 grams. So calculate M is A minus 2Y, where M is 10 grams. So again, it's another calculation. You've got your value for Y. A, it tells you right at the beginning is the distance between the two holes. Again, in the examiner, read the examiner's report, quite a few candidates actually didn't know what A was, but A is here right at the beginning. They seem to have forgotten it, okay? So you calculate your value and then justify the number of significant figures that you've given in your value. Well, you know that all your numbers are 3 significant figures. So this M times A minus 2Y should be equal to 2. Then you're going to add another 10 gram mass. Now, when I give you the paper to do for the lesson after, I'm going to give you fresh values of Y and Y minus X. Fresh values of Y. And then I will, actually, I can give you that already. That would be 41.5 centimeters. So if you've watched the introduction video, you'll know what Y is. Then you calculate Y minus X, and then you then calculate your new value of M times A minus 2Y. So that's a simple bit of calculation, really. The next part is it's suggested that there is some constant there. Okay, so you get your values of k. So you work out what k1 is, you work out what k2 is, because you know that k here is a rearrangement of this. So you start by rearranging it. So it's y minus x over ma minus 2y. Okay, now in your previous question, you're asked to actually calculate that for both of them. So you're just using those values that you've already calculated. And you're looking at your values of k and just need to think, do we need any units? Well, that's a unit of length, meters, or centimeters in this case. Those two are both in centimeters as well. So there's no unit. So we don't bother with a unit. We get our two values of k here. It then says, suggest whether your results support the relationship. So the first thing you want to look for is what these two values of k are. If these two values of k are very similar in your view, then it supports the relationship. So that's what you say. You say that k values are similar in both cases, or you say that they're not. It's only 1 mark, so you just really want something to justify it. So when we say similar, well, we know our percentage uncertainty is probably going to be round about a few percent. So if these two values are within a few percent of each other, or maybe within about 5 or 10%, then it could support the relationship. You then use your relationship to calculate m of the mass, m of the meter rule. That's the second value of k to get what m is. So you just rearrange it to make m the subject. Here, b is 150 grams. So you just work out the mass of the ruler in grams. It's just a rearrangement of that formula. And then this is the bit where you've got to use your imagination a little bit to describe your 4 sources of uncertainty or limitations in the procedure. So the obvious one, because my hint here is to go for what is obvious. So what's obvious here is you've only got 2 values. So you've only got 2 values of x and y, so of y and m. And okay, so the solution is take several different values for different values of mass, and then that's this obvious one. So, but then you want to say what you're doing. You want to draw a graph. Draw a graph of y minus x versus m a minus 2y, and you should get and explain. You should get a straight line, and you can then measure the gradient, which will give you the constant. Okay, that's a simple way to do it if it's correct. So we're then looking at other things that might cause a problem. So what might be a problem, for example, with measuring this distance here? Well, first of all, it's the thickness of the string. If the string's quite thick, you're going to be plus or minus another millimeter. So if you're plus or minus another millimeter, you'd say that the string was thick. And on solution 2, you'd maybe suggest something like having a thin piece of string. So I'd like you to think about what other sources of uncertainty or things that might make the measurements difficult would be. See if you can come up with 4. And then at the end, afterwards, then with each one in turn, state what you would do to actually reduce the uncertainty in those values. So we've only got 2 sets of values. That'll be problem number 1. Take several different readings. That would be solution number 1, and so on. Does that make sense?
Yes.
Okay. Do you reckon you can do that?
Yep, I can.
Okay. So what I'll do is I'll stop recording and I'll let you have a go at doing that. Do feel free to watch the recording again if there are any bits you're unclear on. Have a go at doing that, and then on Friday's lesson, what we'll do is I'll do a walkthrough for this particular paper. Okay, so I'll take you through it and show you what, if anything, was missed. Okay.
Okay, thank you.
Okay, so your next 2 hours of work, which is going to be just the last 15 minutes of this lesson, and then the hour and a half of the next lesson, plus a little bit of homework, is really to get that paper done. All right.
Okay.
All right.
Okay.
I'll speak to you all on Friday.
Okay.